let's go ahead. When you compute these tracked points on a larger image, sometimes even you have a flow description image, something looking like the orientation tensor we looked at in lecture 3. It's sometimes difficult to get the flow field looking nice. That means every pixel may be added some jitter, and for that reason we may want to do some kind of average flow computation instead to get a better overview of where we have our flow vectors. And we can do this by averaging in different ways. You can do it spatially on each frame. You can do it also between the frames temporarily, or a mix of the two, spatial temporally. And for that we need some vectors. So this code is actually producing a table of some vectors that we want to work with. We have the positions and we have the orientation of each vector. And that we want to average now spatially. So that means in every time frame we do some averaging over some area. And the averaging can of course be an averaging, but it's actually better to do some kind of interpolation instead from the field. And what we are using for doing that is this linear ND interpolator. So we take the field, the original field, and from that we can do a rescaling using this interpolation. And for example, we have this dfunc, dx and dyfunc, and saying we want fields of 8 by 8 instead of, I think it was 10 in the original one. And then we get, no, this was only the positions, sorry. And then we get the output for these points. And what we have are these fields. So we have the x position, we have the y position, and then we have dx and dy, and that gives us this vector field, which is not very exciting, but it's good to show the concept on. And when we do the temporal averaging, we are actually doing it instead of on each frame. We're doing averaging from point to point within the frames. Sometimes that has the purpose that you may be a bit too well resolved in your time frames and you want to make it compactor some way, then you can do that. And then you can see that if we have our dx and dy, they are both after the averaging. We are just having actually the same, -1, -1, and that points actually then slightly downward, down and backwards. Then the most complicated, of course, is when we combine the two. Then we have averaging within the field itself and also between the frames. And that gives us then a little bit more robust averaging. And to do this, it requires quite some code, and also there is a little bit animation. And that one should, I should have done, just a moment. I hope this is, hello. Yeah, it came down here. That was a bit stupid, but oops, nay. Yeah, and here you can see how the spatial averaging, that it's averaging in two directions, and you can see also that the field is much more compact, and that is the effect we want to look at. Looking at now a little bit longer series, we have, okay, let's go back on the slides again. I think that should work. Now we have a little more complicated, longer series where we look at how the dots are moving around. So they're moving a little bit upwards, so staircase, and then they're jumping back down. And from that, we can also create some average vector field. And the tracking of that first looks something like this. And you can see how the tracking is actually working quite well. In this case, there are no ambiguities as we had before. And that makes also life much easier. It's probably very unlikely that you have it exactly as it was in the previous result. And now looking at the really complicated series, or actually this is the series that we looked at. dx is moving from 0. In some cases it's not moving at all, and in other cases it's moving -1. And the y is moving 2 steps sometimes, and nothing in the other cases. So it's actually interleaving between moving y and x. And looking at the vectors of this movement, you can see here what is happening as a quiver plot. And that one, yeah. Actually, I skipped the other longer series. If you want to do advanced tracking, it's really a lot of coding. You already saw in these examples that there is a lot of coding to do. But of course, someone else did the job for you. So there is this package TrackPy, which is developed to give you the tools for doing tracking. And here are some examples from their welcome page, where you have some cells that you want to follow. There is this bubble field, and that's actually part of this tutorial, where you can go step by step through a series of bubbles. And it includes all the things. You have the segmentation, you have the labeling, feature point identification or center point identification, and then finally they give you the tools to do this quiver plot showing how the bubbles are moving throughout the time series. So that's actually a pretty nice example to look at. Then they add even more tracking cases, and you can see what they can do with this toolbox. I think this is a good choice if you want to look at tracking in more detail. Problem with tracking. We already saw the problem that we had the same distance and we don't know where to go. But other things is random disappearance. So if you have something that goes out of the frame and coming back again, that is one problem. The other one is if you have, for example, bubbles that after a while they pop and merge together, and then from having 2 bubbles, you all of a sudden only have 1, and then you have to decide what to do with it. Of course, we also have motion artifacts that it's making it blurry and harder to detect which items are the right ones. And yeah, sometimes items can just disappear for some reason. Maybe it dies, or maybe it's burnt out, or something like that. So there are a lot of tricks and troubles that you can come into when you do this tracking. And one is also jitter or motion noise, which is that it's not staying perfectly on the path. So we have the motion, and which has some magnitude and some angles, so you know where it's going. But the problem here is that this one is a random variable, and that makes it not precisely on the position that you would expect. Some of these tracking algorithms, they are working using the the curvature of the trajectory that it has known already. So it's following some trajectory and predicts where the next point should be, but if you have this jitter, it may not be exactly on that point, and then you have to have some robustness that actually grabs it anyway. And well, there are a lot of limitations. It can be difficult to find things in some cases if the flow rate is too high, if the flow rate has a certain kind of characteristics which the algorithm cannot follow. And density is also a problem. If you have, I heard of some people who wanted to do tracking of snowflakes in a wind tunnel, and they wanted to follow the snowflakes, how they move around. Then you have so many items in your image, and you don't. It's hard to really distinguish which one was it, and that is also a problem when you do this kind of tracking experiments. Last one I forgot actually to mention is particle uniqueness. If you have particles of the same shape and same size and everything, it's harder to do the tracking because you can't distinguish them. If they are more irregular in the shape, then it's easier to identify which one is the right one. And how we can now improve the tracking is, one is changing the acquisition rate. One way is changing the flow rate of your process, but the other one is also increasing the frame rate of the camera. And that can also make it easier to handle the jitter because it doesn't move that much over the time. Another thing is also going into the resolution and being able to better distinguish the items. And then you can play with the experimental parameters, like again flow rate and flow type, how unique the particles are you want to investigate, if you can modify it. Also the vibration and temperature changes within the system, and yeah, well, which kind of mixture you were working with when you of this assembly that you're investigating. So there are, on one side, the acquisition you can modify, and on the other side, you can also improve or change the experimental parameters, and together you get the ideal system for tracking and following these processes. You just have to be, when you change the experimental parameters, you just have to be careful that you don't change them too far away from what you really wanted to investigate, just because you want to follow some, be able to follow it. There were some examples where they worked with, they started looking at sand and soil and water distribution, and in the end they came up with working with glass beads instead, but glass beads have completely different characteristics, and that became a sub-science of itself, looking at the water distribution among glass beads, which wasn't related to the original problem at all anymore. What you can do to check how well your model is working is to do some basic simulations. So here we have some flow, looking at some particles that are moving. Each colored line here is the motion track of the flow. And then we can add this random variation to the flow and seeing how well the tracking still works when you add this uncertainty to the measurement. And with that, you can also improve the robustness of your algorithm for the tracking. And the simulations, they are actually good because they can help you to understand how you should design your experiment. So you can determine what is the particle density you can work with when you want to do this kind of tracking. Also which flow rate you want to work with. All that is information, and also, of course, the jitter that I mentioned before. All this information you can simulate, easily changing parameters and see in what range you actually can do your experiment with the tools that you have available. Here is also not mentioned the noise levels, but that of course also come into play when you want to do this analysis. And again, we have to decide what is enough. So, for example, 5% in bubble position may be less than a change of 5% in the flow field, or maybe 20%, given more than 20% of error in the topology. So you have to decide what is the information you want to extract in the end. And also, if you have a 5%, so these are just examples, 5% error in shape or volume, that would be a different of 5% in distribution or changes. Maybe the individual bubble changes by some amount. And if you look at the strain tensors of the bubbles, it may give you more than 15% effect. So the errors, they're propagating depending on which parameter you are looking at. And that is something you have to be aware of when you plan your experiment. And we could also, in the tracking, as I mentioned before, extend the nearest neighbor criteria, looking at different neighborhood and how the particle hangs together with it. So here you want to have a double criteria where you have the first the nearest neighbor, and then you have looking at the second one as the neighbor of, so actually the reverse more or less. So taking the estimated and looking at the next one. And hopefully you should have the same points. You can also look at maximum displacement instead of looking at the Euclidean distance. And if you want to go really advanced, you can also do this prior prediction where you follow the trajectory of the tracked particles, and then you have to keep in your history in the modeling. And one way of doing it is to use the derivative, and extending it really advanced is going to use a Kalman filter for the particle tracking. The Kalman filter is using a combination of probability and the derivative to determine where you should look. And important here is that it, depending on the uncertainty, it also changes the search region of the matching point. So that's the big hammer if you want to do tracking. It's been actually used, for example, in radar technology when they want to track different airplanes on the screen. They can actually, with the help of Kalman filters, they can project the trajectories of how different aircraft are moving around. So we have a lot of different alternatives. So mostly you need to do a combination of multiple hypotheses to be able to define which one is. And the problem is very much when you have merging and splitting particles, what to do with those cases, and define a strategy for that. And that can be tuned a little bit by this multiple hypothesis testing, but yeah, it's getting into the complex models, and that is something that also is handled by this TrackPy package. Now to a different way of tracking motion. If you can't identify really sharp features that you can track or clear items, you can work with correlation instead. So looking at the image intensities in different regions. And the correlation is you have two images, I0 and I1. And I1 is moved by some vector or position. And the nice thing with the correlation is you can also compute it in the Fourier space by multiplying the Fourier transform of the two images, and one of them is the complex conjugate. And that can be visualized first in 1D, where we look at two signals. We just have two peaks, which are displaced. And if you compute the Fourier transform of the two, and this complex conjugate, and transform it back again, then you get a new peak, and the displacement of that peak is actually the distance that they have moved from, that they are separated apart from each other. This can of course also be used in 2D, and this is some test we can do with for example this 5 from the MNIST data set. And as you can see, we have it shifted here by -3 and 2, so it's up towards the upper right corner. And now we want to see how much displacement we have between these images. And in real space, what you're doing is more or less that you move one image over the other and compute the sum between the two images, multiply the image and compute the sum of the result, to get some point, some measurement value, and then you have to scan the whole image, doing that for point by point. And you can see that with this, there is a hotspot down here in this region, and that would correspond to the displacement of your image. We can also use other metrics. We can use mean square error or root mean squared error and look for minima. That would be another alternative when you do this scanning in the real space. And here is some new code to do this. And I think this one I need to execute actually. So, and no, that wasn't good. Okay, sorry for that. I need to go back a bit. No. Yeah. Something is not working today. That's stupid. Ah, there it comes. Yes. And just for safety, I do the other ones. So now I can go back to what I wanted to show. Yes. Okay, sorry for this interruption. So, when we look at the mean squared error, it appears that we have a little bit confusion. We have two positions, and the most intense one is actually a mix between the rotated images. So we have the upper part and the lower part apparently gave the greatest or the best result in the mean squared error, which is a bit confusing. But we can also look at the correlation using the Fourier transform of this image. And you can see nicely that it actually produces a peak here in the correlation image, which corresponds to 2 and -3. So this one worked pretty well. If you look at the Fourier transforms of the two images, looking at the amplitude, you won't see very much difference between them, because the difference in displacement lies in the phase image. I don't show the phase image because that's just confusing. You don't see. It's hard to interpret, so there is no point in showing it actually. But the displacement information is within the phase angle between the two complex components. Yeah, so we get a nice dot here that tells us where to go. And then we can try with the bone image. Again, we have the displaced bone slices. And now we just look at a little subsection of it. It's actually just a very small area to look at the details, because otherwise it's too cluttered. And looking at what the correlation does, it computes the values, and hopefully we get an intensity maximum that corresponds to the peak where we want to go. This is harder to interpret because we have now just grayscales, and it's probably nicer to look in the large result, in the large image. So let's, I think this one is also, oh, hey. That one should be executed. Yeah. And here we have the large one. We have minus 15 and 15. And the mean squared error in this case gave a very nice point that we can locate for this displacement. So depending a little bit on the content of the gray level of the images, you should probably use a different metric to compare the images. And that is to be explored when you look at your specific images. We also have the sand grains, which we can look at again with some displacement, and we can look at those looking in the Fourier space and like that. And here we also have a very distinct point that tells us about the displacement. Here it is shifted by half a pixel, and that's probably just because of the accuracy of the grid that we have available that makes this confusion. So that can be adjusted. Registration is another thing that is very important when you work with the time series of images. And the purpose of registration is that if you do two images, sometimes under very different conditions, they may be flipped, they may be rotated, they may be displaced. And as you see in this chest X-ray, it's moving around. Sometimes there are some tubes, sometimes it's in a better or a worse condition. And the task of the registration now is to have these images and making sure that, first of all, they are flipped in the right way. And then with the registration, you should match them, that they are overlapping and on the same coordinate system. That can involve different operations. So one is, of course, the flipping. The next one is the translation. And then you have the rotation. So we have a set of operations that we want to perform on the image. And typically you have one fixed image, and then you have a moving image that you want to move into the fixed one. And what we need is a set of components. We need some image transform. How that is defined is up to the task. So maybe sometimes it's just a translation. Sometimes you need a full affine transformation with skew and warp, and sometimes even having a non-rigid transformation. For example, in particular, the body is moving and changing shape. And then you may have to even change the grid of your registration. And then you need a metric or a loss function. And finally, we also need an optimizer that drives you to the right point. And that can look something like this, where you have a moving image, you have a transform and an interpolator, and then you compare the result with the fixed image. So that could be one way of displaying this. And that one doesn't show up. Okay. Let's go again. And there are different ways of doing this. And I want to show a different one. It could also look something like this, where you have the fixed image, which you compare. So it's actually just wrapped around a bit. But the important component here now is that you also have an optimizer that controls the transform. And for that, you have the whole algorithm that we need to do. And the optimizer is comparing the transformed moving image using this metric compared to the fixed image. The metric can be different things, and we're going to look into that just about in the next slide. So again, we have the fixed images and the moving images, and that I already said. Transforms, what we have are a lot of operations in order to get the images into the same grid. And next week I'm going to also talk about registration a little bit, but in another context than in the time series. Then we have the interpolator. Depending on the accuracy you need, you can have different types. You can have nearest neighbor interpolation, bilinear, bicubic, B-spline, whatever you would need to get the accuracy of your interpolation from this transformation. The metric, we start out with the most simple one. Mean squared error is a very easy one to compute. Then from lecture 3, we have the SSIM, so the simultaneous similarity metric. And we can also use a correlation factor between the images to see which one is when we approach the right registration. And finally, we also have the optimizer, and there is also a bunch of alternative. So gradient descent is a classic one used for this. Adam and stochastic gradients, they are common in machine learning. Not so much, the stochastic gradient used for registration in a couple of packages, but Adam is maybe a little more an outsider in this case. And then we have two more, ADA grad and ADA delta. These are optimizers that are available, for example, in TensorFlow, and can be used for this purpose. So let's look at our tracker. And we have some kind of optimizer for the grid search and the transformer, which acts on the moving image. And then we have the interpolator, and then we compare our metric, which to begin with is mean squared error. And what we are looking at now are two fragments of the bone image that we have used before already. So we have these two, and we want them to be registered with each other. Now, this piece of code is something that I'm not so happy about. From the original version of these lectures, the registration was done in TensorFlow 1. And meanwhile, TensorFlow 1 is deprecated, and I can't use that code anymore. I tried to implement it in TensorFlow 2. And I have the components here, where we have the affine transformation. We have a loss function, which is the least square error. And then afterwards, we run it, computing some gradients, and run those into, they're not showing up, the optimizer, who then provides the parameter set that we want to do. Now, unfortunately, I couldn't manage with the time I had to update it, but this would be the workflow. And my problem lies in that the gradients are not accepted by the optimizer, or the gradients are not working in the way they should. but the basic concept of this code should be this. So I'm sorry about that. But I have some recorded. No, I should have a movie now. Hey, where is my mouse? From the previous results, I actually saved the movie so you can see how the motion is working, how the optimizer is working to get the image into the right position. And you can see now here how this blob is easy to follow, how that one is moving towards this position. And you can also see the mean squared error, how it's reducing with time. It's the mean squared error seems to have a little bit trouble here because it's not managing to move all the sample in the right position. Another alternative would be to work with a different gradient, and in this case we are working with segment the image into a gray level image and then compute the distance field to create much sharper peaks in the image, and that would be like you have some hats moving around, and when they exactly match, then you have the best fit, and that would be an idea to run on that structure. Another option would be to work with the structural similarity index, and let's see what that does. Doesn't really help as much. It seems like it's more jumping around, and it doesn't grab the work pretty well. I think right now this code is a little bit jumpy. But the basic concept of the algorithms is that you have these components that I try to implement. And if you want to work with the registration in general, it's usually better to work with packages like ITK or simple ITK, which you can import in Python. And there is even a separate package called elastics and simple elastics, which is based on the ITK code. And those can be used very well for the segmentation task. Registration task. Sorry. And here is a code example. It's turning into quite lengthy code when you do simple ITK and ITK in general. One feature of it is that you can actually have a parameter file where if you know what you want to do, you can use the parameter file where you have described the typical setup of your registration, and then you don't need to write that much code anymore. So that simplifies the work. And using simple ITK, it does some registration. It seems like it actually wanted to rotate it, which is a bit strange. And another example is that you work on the sand data. Here it seems like it's doing a quite good work, but still it's not perfect. So we need to, actually I need to improve this part of the code. Another side of the correlation is, let's see, here, yes. When you do correlation, we did it until now, we did it on a global sense. But what if you do it on subregions instead? The effect is that then you would have correlations showing how much is the displacement in local regions. And this can be very useful if you want to compute strain fields within the material. And it's used a lot in mechanics, that they use the digital image correlation or volume correlation to determine strain fields within the image data. And looking at a correlation term, and from that you can also have a deformation term within in the data. And that's a lot of text. But in principle, what we want to do is we want to quantify the deformation within your sample. So the deformation is a change in distance over the distance. And that is here just defined as 1D, but we can also extend it up to voxel data. And then from that you can compute the strain tensor, really seeing how the sample is deformed. And there are packages right now, I don't remember what they're called, but there are packages that actually also compute the strain field within the images. And one example of that, you have here different strains. You have the volumetric strains and deviatoric strain. So that would be the change of size and scale, and then you have proportions within the objects for the other one. That is independent of the final scale of the data. And here is a nice experiment, was done by some of my colleagues many years ago, meanwhile. But what they had was a column, I think it was sandstone, and they had 2 notches marked up, and they added load and introduced also some water. So they did a combined experiment with X-rays and neutron, which is actually a transition to next week's lecture, where we're looking at using different modalities in the analysis. But what I could see here is the important information is that they have a shear band within this sample caused by the load, and also they could see the water distribution in this area changed compared to what it was in the unloaded case. So this is a quite nice example of how you can use digital image correlation to analyze images. Actually, I don't have the citation here. It's work by Steve Hall, who is now in Lund. And the experiment was done in Grenoble at the imaging beamline there. And that brings us to the end of today's lecture. So we have talked about dynamic experiments, how we can track different objects, registration. I'm sorry that the demonstration of it wasn't that good today. I need to work on that part. And the final part is when we take the correlation, working with it locally, we can extract information about deformation and strain within the samples. And yeah, next week, as I said, will be about bimodal experiments and also some software engineering, how you should work with your coding a little bit. And so it's not really how you program, but how you organize your programming. And yeah, that will be the topic of next week. So thank you for today.